the old primaries and the new primaries for the color matching function. So everything that relates to the original color to a new color becomes some kind of a translation, matrix translation, 3 by 3 translation. And the relationship in by 3 by 3 is simply defining the translation from one to the other. So now if I know what the translation is, then I can take any color that I get, apply the translation and go to a new color set. And that's how I can equate things together. I can basically normalize everything and bring everyone into a common transformation set. So these, when we bring them into a common transformation set, are also referred to as metamers, right? So you can have two spectra, T and S. Right? They are actually perceptually matched to each other. They will be matched where T will be equal to CS, and C is the color matching function for some set of parameters. Right? So for example, what happens is that this is an effect of taking some T, okay, being multiplied by your mixing matrix or your color primary matrix, and you end up actually getting the integral to be the same. So you could have scenarios where you can take very different light sources with very different spectra, but they will be perceived to be exactly the same. So for example, you can go out and, the simplest example of a good metamer is to go out and buy light. And you want to go out and buy a light source that mimics the illumination of the sun. It's possible to go back and regenerate the exact spectra of what the sun is emitting in terms of energy. But you can actually measure that color and generate a metamer of it, which is the same integral response to color. It's just that you need a new spectra for it. Right? So while E and S can be different, the realization of multiplication with C gives you the exact same response. So that's how we can recreate multiple light sources that give you the same effect. Now, how do these things work in the eye, right? Of course, the eye doesn't actually do this. The eye, the sensing system, is relatively straightforward in the sense that we have discrete sensors in our eyes, and we have discrete sensors that are receptive to different wavelengths of light. Okay, so if I look at what my sensors are in the eye, basically they are made up of rods and cones. Cones are the ones that are actually responsible for color sensing. Rods don't really provide us with color information. They're purely there in order to sense the integral amount of light that's coming in. Okay? Now, in general, cones are concentrated around the fovea, the center of the eye. So your peripheral vision is kind of weak in terms of color, right? Almost all the color we sense is based on our central vision system. Okay? Now, the sensitivity of rods and cones is very different in the sense that you get sort of more in terms of darker illumination. Rods are the ones that provide us most of our sensing. Cones are the ones that are actually provide us most of the sensing in terms of normal illumination, ambient illumination, daylight conditions, and so on and so forth. Okay? And that's one of the reasons why, in general we can't read in dark, because in the dark, you are mostly functioning off of your rods. Keep in mind the rod are basically absent in your central foliation, so when you're trying to read something, you just can't see it because the amount of light coming off of that is so little that some of it is being perceived in the peripheral vision, but nothing in your central vision. So it becomes very difficult for us to read in low light conditions. Now, in terms of primaries, our main sensors in the eye, the color sensors, which are cones, they also can be thought of in terms of primaries, 3 primaries. Right? And in fact, that's what we have, 3 discrete types of sensors. LMNS for the long range, medium range, and the short range sensors that we have, which are capable of sensing sort of in the blue range, the green range, and the red range. So they're not these nice cartoon spectra, they're continuous spectra. Right? So they overlap. And in general, the ratio of these sensors that we have is such that you have a lot of sensors that are sort of in the long range. So red sensing, a fair amount in the green sensing, and of course in the blue sensing we have very, very few. In fact, in the main center of the fovea, we almost have no sensors that pick up blue light. We predominantly operate in terms of red and green sensing. Okay? So if I were to look at a cone mosaic, right, a distribution of sensors in the cone, the distribution of cones in the fovea, this is kind of what it would look like. You see that the center is mostly all red and green sensors, no blue. And as you go away from the center, you start seeing more blue sensing cones. So for us, the color perception that we get is actually the integral response of all these cones. And in general, it will be some power response coming from all the cones. It will be some curve over all the wavelengths of light coming in. And this continuous curve will define the kind of color response that your brain provides. Okay? So rods and cones, they kind of act like filters. And in order to get the response of the filter, you're going to multiply essentially the response curve of each sensor with respect to the spectrum of light that's incoming. When I say multiply, it's actually not multiply, right? It's convolution. It's convolved. Now, the question is, does each cone yield one number? Right? Well, we can think of it as one number because it's actually an integral response, right? The perception of color for the brain is instantaneous. So we perceive it at an instance as a result. It's an integral measure over what you may call unit time. So that, from that perspective, is one number coming off of it. Of course, in reality, that number is changing with the, let's say, whatever the unit time is for the firing of the neuron. So now, of course, the obvious question is, if that's what we think color is, then from the digital image standpoint, we don't have this nice continuous response. We simply are providing this as 3 numbers. So how do we go from this curve to 3 numbers? So one solution to that is to say, well, I would like red to be this 600 to 700 bucket. So I'll integrate the amount of energy in that bucket. Maybe that's the number I report as my red color. So I integrate things within each bucket and report that as a single value. And that's how I come up with red, green, and blue assignment for a digital image. So, yes, very good. So how do we get a single number as opposed to something that's changing, right? But from a digital representation, remember what we have done is already generated this profile is an integral of exposure time.